I'm very happy to introduce Professor Shobhana Narasimhan today. She's an eminent physicist from Jawaharlal Nehru Centre for Advanced Scientific Research. Her research is mainly in the area of condensed matter physics and specifically on density functional theory. We are very happy to have her here on campus, giving our science seminar. And welcome.
Thank you, Kripa. I'm very happy to be here.
So, how are you feeling today, Shobhana? How was your visit on campus?
It's been great so far. I knew several people on the faculty, was intrigued by the philosophy of education here, so wanted to visit. And so when I was asked to give this DA C.V. Raman seminar, and the IPA told me that I could choose any institution in Bangalore, I immediately chose to give it here because I thought finally this would give me an excuse to come and interact with people here.
Yeah, that's great. We are very lucky to have you here on campus today.
And I must say I really enjoyed the morning session where I talked to several of the honors students and learned about their projects. I thought they were very smart and very enthusiastic. I was really impressed.
They'll be very happy to hear this. So perhaps, Shobhana, you could tell us a little bit about your research and what excites you about it.
So I work in computational nanoscience. I want to understand why materials have the properties they do, and then use this knowledge to design new materials with targeted properties. And to do this, I use a technique called density functional theory. I find it very exciting because I think we've finally reached a place in the development of this field where experiments and theory have really converged, so that when someone does an experiment, we can really do a calculation which can understand what they have seen in the experiment, explain it, interpret it. And at the same time, when we do a calculation, people can do an experiment that confirms our predictions. And so this to and fro between experiment and calculation, I think, is really exciting. There's a synergy between them, and that's something I enjoy very much.
So for our audience, which is a little broad, could you maybe give an example of how density functional theory is actually relevant in their own life?
Okay, so there is something called the Haber process, where nitrogen and hydrogen are combined to make ammonia. This is something that probably everybody studied in school, but didn't think was particularly important and promptly forgot. But it's one of the most important industrial reactions. I think 1% of all energy consumption in the world is taken up by the Haber process. Also, half of all the nitrogen in our bodies, it's estimated, has gone through the Haber process. And it's really a very important reaction to produce fertilizers to help us grow food, etc. And for this reaction to take place, one needs to find a catalyst over which the nitrogen and hydrogen combine, and people use iron, but it's not all that ideal. For the reaction to take place, you need very high temperatures and pressures, and this means it consumes a lot of energy. So, for example, from density functional theory calculations, people have found new catalysts for this. A few plants have switched, I believe, to using these new catalysts. People are also using density functional theory calculation to see if we can have the same reaction happen electrochemically, so that you don't have high temperatures and pressures necessary. So this is an example of something where DFT can be used. Also, I think increasingly DFT people are starting to use it in things like drug design, where you can design drugs, etc. So there are many, many things. I mean, materials are really vital for us. We need new materials to make computers, to make chips, to purify water, to generate electricity. There's so many things for which we use materials. And these materials can be designed using density functional theory.
Perhaps you could tell us a little bit about the challenges that you think people face in this particular field. What are the current challenges?
Okay, so there are some challenges which I would say are theoretical challenges and some which are sort of computational challenges. The theoretical challenge is that this is a theory which in principle should be exact, in the sense that when you do a density functional theory calculation on a material, you should get exactly the same answer as when you do an experiment on that material. But this is not always the case. And this is because this theory, which formally should be exact, in practice is approximate. So we have to get better and better approximations so that the theory becomes more and more accurate. The other challenge, I would say, is a computational challenge, because when we do these simulations, right now we can simulate systems which have thousands or tens of thousands of atoms, and we can simulate them for a time that's only 1 femtosecond, that is 10 raised to minus 15 seconds. And that's a very short time. That's a rather small system. So if we could have more faster computers with more memory, etc., then we would be able to tackle larger systems, more complicated systems. Many of these challenges people are now trying to overcome using machine learning instead.
So actually that comes to the next question that begs asking. So in today's time, we have this all-pervasive AI and ML, and how is that impacting the field?
So I think it's completely changing the field. About 2 years ago, we had a meeting called Nanoscience in Bangalore, where most of the practitioners of DFT in India gathered. And we did a little survey and we asked them how many of them had started using machine learning in their work. And 2/3 of them said they had already started using it. And by now, I think that percentage would be even higher. There are lots of different ways in which we use machine learning in the field. For example, I said there are certain things that we do approximately, but in principle should be done exactly. The technical name for the main approximation we make, there's something called the exchange correlation functional, which sort of a lot of the mystique, if you like, of DFT subsumed into that. And we know an exact exchange correlation functional exists, but we don't know what it is. And so people are trying to learn that exchange correlation functional doing machine learning. Another thing people are doing is it's very expensive computationally to do a DFT calculation sometimes. So instead of always doing a DFT calculation, you have a big database of results from DFT calculations. You train your machine learning algorithm on those results, and then you can make predictions for new materials, new systems to consider, etc. And for some of these, you won't need to necessarily do the full DFT calculation, or at least you can make a short list of systems which would be worth examining instead of having to just do calculations on lots and lots of systems.
So do you see it as more of a positive thing, or do you think there's a flip side to it as well?
So this is actually a very controversial question. I think you will get very different answers from different people in the field. I think it is a positive thing in that it is advancing the field and that we're getting more and more answers to questions. But the answers are perhaps different from the traditional kinds of answers to questions we were asking. For example, if you say, I want a material that can do this, 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 machine learning may tell you, okay, here's the material that you should make. But it may not necessarily tell you why that is the best material for this. So a lot of these why questions you cannot get from machine learning. There's a lot of stuff that goes on in the innards of a machine learning algorithm which we can't understand or know or interpret. There's a lot of black box, black magic, according to some people. And if we are sort of classically trained as people of my generation are, classically not in the sense of classical versus quantum, but we are trained to think that your role as a physicist is not only to find out what works, but why it works and to gain some deep understanding of it. That we do not seem to be getting much of with these new machine learning approaches. And many people find that very dissatisfying. One of my students also has been telling me that she finds it intellectually dissatisfying to use ML. She would much rather work out something with pen and paper. I mean, already there were people who, when we made the transition from pen and paper physics to computational physics, were dissatisfied. And now I think we're having another transition to machine learning and artificial intelligence, and people are getting dissatisfied. But I think this is it. I mean, it's going to happen. It is happening, has happened. We just have to live with it.
So, Shobhana, other than your scientific research career, you've been a very prominent figure in the Indian physics space, being a woman physicist. So, I was wondering if you would like to comment about, how institutes and universities of higher learning could support underrepresented minorities joining science or research.
So I think we have a lot of problems about underrepresentation of various groups. Women is an obvious one. We have about 10% of physicists in India are women. That is, if you look at working physicists. If you look at PhDs, the number is much higher. But if you look at people who are, say, teaching or researching in universities and institutes, it's only about 10%. This is a problem that people are at least beginning to acknowledge now. You hear people mention it. You hear people, they have seminars about it. They have committees to talk about it. I still think not much is actually being done about it, but to start the conversation is at least the first step. I think what we are not even acknowledging is that we have underrepresentation in other ways, in terms of caste, religion, people with disabilities, things like this. In many of these cases, these are not visible minorities, because if you look at a group at a conference and you see there are no women there, or there's only one woman there, that's very obvious to everyone. But you cannot just look at a group of people and say, okay, other disadvantaged groups in terms of caste or underrepresented religions, that they're not there. And so I think this does not get discussed as much. And I think the first step before you do anything about it is to acknowledge that this is an issue, and then to start discussing what can be done about it.
Often scientists confine themselves to their research and, rarely engage with public debate. So do you think scientists have a role in public policy or having a public say?
Yes, in various ways. One thing is, first of all, we all feel we should get funding for our science. And that is becoming increasingly difficult these days. And I think part of the reason for that is that we do not take enough trouble to tell people what we're doing and why it is important. And if we do not do that, the general public does not understand why what we're doing is important, and nor does the government. And so I think, at least for that reason alone, if for no other reason, we should do it. I also feel that we have a social responsibility. Now, this is kind of a tricky question because I also feel one should do blue sky research. I feel one should do basic research. But some part of the scientific community at least should address societal problems, I think. That is for each individual scientist to decide what kind of science they want to do. But that is something that, again, we need to interact with the government and with the general public about. The other thing is, see, we are trained to evaluate scientific data. We're trained to evaluate scientific publications. But we should share this training with other people. Like, you see it now that, for example, when there was COVID, there was so much fear, so much misinformation. Should you get the vaccine or not? Should you wear a mask or not? And of course, there are people who work in epidemiology or infectious disease research who are directly concerned and can answer these questions. But even those people did not often bother to communicate with the public. And the rest of us also, I mean, we can in principle put in some effort to read the literature in those fields and try to understand and then share this knowledge. I mean, the fact that people are so scared of vaccines or in some countries refuse adamantly to mask, that shows that scientists have not done what they should, I think.
If there's one thing that you can change about doing science in India, or one or several things, what would they be?
Okay, this is a very... I wish you hadn't asked me this question.
Oh, no.
Okay, let me tell you a story for a slightly different, almost same question.
Okay.
I gave a talk at a certain institution in India, which I will not name, and the director asked me if I could change one thing that would help increase the number of women doing science in India, what would I do? And my answer to that was that we should change this idea that science is something you have to do 24/7. I said we should acknowledge that you can do very good science even if you work from 9 to 5 and only on weekdays, because it is this idea that you have to do it all the time, I think, reduces the number of women choosing scientific careers. For what it's worth, the director said, I don't agree with you at all. So that is one thing that I would change.
The romanticization of the hard work and suffering and that kind of thing, basically.
I wouldn't call it romanticization. I would call it machismo. I mean, this idea, because see, nobody really works 24/7. I mean, people who are in the labs day and night, I mean, they can't actually be working all the time. They spend a lot of time, gossiping, looking up other people's age indices and drinking coffee and, browsing the internet. But the fact that they're there, they think is somehow, they get brownie points for that.
Being present in that space.
Yeah, and they make fun of those who are not. And I think that's very wrong. So that is one thing I would like to see change in the culture of science. Of course, I would like it if there was more funding for science in India. As a percentage of our GDP, we spend not enough. And it would be nice if there was more funding for science in India, I think.
Thanks a lot for joining us today.
Thank
It was
you.
lovely talking to you.
Thank you.
Okay.